Good morning, everyone. This is my honor to present our work in this wonderful workshop so that we have a chance to know each other and for possible future collaboration. The title of my talk is Construction of Hetero-Dimensional C-ZnO molybdenum disulfide mesoporous carbon nanocomposite for visible light-driven photocatalytic activity and enhanced durability. My name is Da-Ren. I work in the Department of Materials and Optoelectronic Science. Very short brief of my area of interest and activity. In the past, I worked in several fields, in semiconductor optics and semiconductor transport in semi-classical and quantum regime, and semiconductor materials for optoelectronics, and hybrid nanostructures for energy storage and conversion. I also work on nanomaterials for biomedical technology and thermoelectric materials. Relevant techniques include wet chemical synthesis, gas phase synthesis, structural, elemental, and optical analysis, electrochemical analyzer, and Seebeck coefficient and conductivity measurements. Now we talk about semiconductor catalysis science. This technique converts solar energy to chemical energy or solar fields for many applications via reduction and oxidation reactions, to name a few: water splitting and CO2 reduction. The basic process of reactions are threefold: the photo-excitation of charge carriers, the charge separation and transfer, and the surface charge utilization. However, the quantum yield is generally low. This is due to the much faster kinetics for charge carrier recombination than that for interfacial charge transfer. Only a small part of the photogenerated carriers can migrate to the surface reaction sites. To improve quantum yield, materials engineering strategies are crucial. Here we list 6 ones. They are Schottky junction, type 2 heterojunction, Z-scheme junction, quantum size effect, pole-textural tearing, co-catalyst loading. For instance, in the use of Schottky junction, we emphasize several factors like plasmonic effect, nanocarbons, noble metals, metallic single-layer TMDs. We also emphasize the construction of nano-sized semiconductors that embrace quantum size effect, including bandgap tuning, increased surface area. These are so meaningful for performance enhancement. This example shows how the nanostructuring of C-ZnO modify their bandgap and the surface area to a large extent. In addition, co-catalyst loading is another essential approach. It can prolong the carrier lifetime and enrich reaction active sites. In this work, we start with a versatile semiconductor zinc oxide-based photocatalyst to acquire an improved quantum efficiency. A few techniques based on previous reasoning are useful, such as metal doping, dye sensitization, conjugate polymer modification, and semiconductor coupling. Here, we want to additionally emphasize the use of carbon in our proposal. There are several possible roles for carbon in a composite. First, they can act as a solid support material. They can also serve as electron reservoirs, or they could hinder the photocorrosion of oxide semiconductors. And a tiny amount of carbon could impose the doping effect. Here we propose that the coexistence of mesoporous carbon, C-doped zinc oxide, molybdenum disulfide nanosheets may form a promising architecture for efficient photocatalysis. We set up a 2-step synthesis protocol to prepare the ternary composite, which shows superior photocatalytic efficiency and recycling stability. We first prepare C-ZnO MPC binary composite by wet chemical method. In this work, the carbon content is very important. We need to tune the sucrose content to the best condition in advance. The binary composite shows a three-dimensional mesoporous carbon structure assembled by interconnected thin sheets with a dimension of micrometer. Spherical zinc oxide nanoparticles are spreading over the nanosheet surface. For comparison, the pristine zinc oxide are monodispersed and spherical nanoparticles. Next, we prepare few-layer molybdenum disulfide nanosheets by LPE technique. This dried exploited 2D molybdenum disulfide nanosheets shows plate-like geometry. They are entered on the binary composite by wet chemical treatment. This gives the ternary composite. We've seen very thin molybdenum disulfide nanosheets incorporated in the composite. This porous 3D skeleton is beneficial for solution infiltration, reduced carrier diffusion lengths, and with abundant active sites. The constituent elements were confirmed by Edx and Elemental Mapping. The TEM shows the quasi-0D 2D structure, in which many zinc oxide particles are interdispersed on thin carbon sheets. The hexagonal Wuchai face of zinc oxide can be confirmed by the resolved fringes spacing in HRTM. The 2D molybdenum disulfide nanosheets have a lateral size of 100 to 200 nanometer. The SAED shows the good crystallinity. The ternary nanocomposite shows similar quasi-0D 2D nanostructure. The HRTM image shows it's composed of the molybdenum disulfide, the zinc oxide nanoparticle, and the carbonaceous layer. The X-ray diffraction pattern shows the correct structure that we prepared. We want to say that the amplified SRD patterns of carbonaceous composite shows diffraction peak shifts. It may be due to the substitution of oxygen with carbon and the formation of ZN-C bonds during the synthesis of C-ZnO. The substitution of carbon atom would eventually expand the zinc oxide lattice. It suggests that the C-doping took place. In XPS study, for O1s spectrum, in addition to the lattice oxygen, we have seen another feature for ZN oxygen vacancy and ZN-OC bonds. For C1s spectra, apart from usual CC-CO bonds, one peak at 285 electron volt is associated with ZN-OC bonds. It means the carbon was in the interstitial sites. There's another peak at 283 electron volt, which is associated with the ZN-C bonds. This is the defect complex involved oxygen vacancies. Our X-ray diffraction also suggests that the possible ZN-C formation exists. The XPS result shows that the carbon was doped to the interstitial position of the zinc oxide lattice, and its possible defect complex involves ZN-C and oxygen vacancy. The orbital hybridization of ZN-OC bond results in the formation of an intermediate band. It can activate the visible light absorption in the carbon-doped zinc oxide. In the molybdenum 3D spectra, we confirm the MO4+ state. We also observe the presence of MO6+ state, which is due to the slight oxidation. We have carried out the UV visible absorption study. The pristine zinc oxide is only responsive in the UV. The redshift of absorption into the visible light region is evident for the carbonaceous nanocomposite. Here, the band gap, or the optical band gap, shows apparent redshift into the visible light region. we test the photocatalytic activity. We found the ternary composite shows the best performance under visible light irradiation. The reaction dynamics follow the first-order kinetics, and the reaction constants can be obtained. Another ionic dye, MO, was also tested, which can also shows that the ternary composite shows the best performance. We carry out the stability test under UV irradiation. The ternary composite shows excellent stability. However, the pristine zinc oxide suffers from large loss in this test. We also check the structural integrity after use, which shows the good performance. We also tested a hazardous material in wastewater, phenol. The removal efficiency is pretty good for the ternary composite. We carry out the total organic carbon measurement to investigate the mineralization of MB and nitrobenzene. The residual amount of TOC after reaction is very low. This verifies the removal of organic compound by the photodegradation. We show the PO quenching for carbonaceous nanocomposites, which shows efficient interfacial charge transfer. Transient photocurrent responses also shows similar results. The EIS result further shows that the ternary composite has a much lower charge transfer resistance. The scavenger test told us superoxide or hydroxyl radicals are primary for the reactions. We show the illustration of the proposed photocatalytic mechanism. The photo-generated electrons spread throughout the carbonaceous support and reduce the dissolved oxygen to form the superoxide radicals. They can react with water molecules and further produce hydroxyl radicals by these reactions. On the other hand, the holes were left in the valence band of semiconductors and generate reactive hydroxyl radicals by these steps. Finally, the generated active radical species react with the organic dyes to form the degradation products. We know that under UV irradiation for a long time, holes from zinc oxide nanoparticles in solution could react with surface oxygen and result in the photo decomposition of zinc oxide. In our composite, holes from the embedded zinc oxide are consumed in the photocatalytic reactions, and the competing dissolution process of zinc oxide can be suppressed. Finally, messages to take away or summary. The carbon has many roles that benefit the photocatalytic efficacy. First, we showed a unique 3D mesoporous structure, which shows large adsorption capacity, high porosity, and the large surface area. Second, defect engineering can be applied. Third, it works as a support for co-catalyst loading and facilitate heterointerface engineering. Fourth, for interface engineering, it works as a photoelectron reservoir. Thank you for your attention.